And the good point of getting talk at the end of the conference is most of the concepts are almost done, right? So people are all full with all the necessary ingredient to understand quantum matters. So I would like to thank organizers for giving me and my group this opportunity to talk about some of the recent results which we have got regarding non-reciprocal magnetotransport in chiral tellurium nanowires. Just one suggestion to the organizers: please give title of the talk in the plan. It's very difficult to know who is talking about what prior. Okay, anyway, so so this work was in collaboration with Professor Atindranath Pal, he's present here, SN Bose Center, and Matthew Pierre from High Magnetic Field Laboratory in Toulouse. You would understand in the course of the talk that why this field is necessary. So that is why we need to collaborate. This is purely a collaborative work. And the PhD student who is involved in this work is Vipul. So let me start with chirality, which involves when you measure resistance of a centrosymmetric crystal, Onsager reciprocity works. So R plus I is equal to R minus I. But what happens if the crystal is non-centrosymmetric and chiral, let's say? So a current knows which way it is flowing. Of course, then resistance plus I is not equal to minus I. So whatever we are talking, the end result, I have to show that some resistance which we will measure is not reciprocal. So, so this is the expression of resistance as a function of field and current. So we are familiar with this term. So we are introducing this term as the chiral term. So usually chirality comes from spin orbit, Berry curvature, asymmetric scattering from impurities, and electronic band structure. So this is the main significance of this chirality, which flips sign when current reverses. So as you can understand, it can have plus or minus 1 term. Of course, it depends on the Berry curvature, and three terms which governs this chiral nature of the transport is hidden symmetry, spin and orbital texture, and you can apply this for passive rectification. So diode-like behavior. Is it something new which we are probing? Actually not, because people have done beautiful experiment. You should read this experiment where they make helices and put bismuth. And since these are mechanical helices, so they are formation is like a helix, and they measure resistance. As you can see, for a specific magnetic field, plus I and minus I is different. You can compare the resistance values as a function of field. So, as I was discussing, linear response is always like this. The conductor is direction blind. Non-reciprocity, the second order term, usually second harmonic term is the fingerprint. So you can measure something like Berry curvature, nonlinear Hall, or magnetochiral effect. So what type of broken symmetries is essential for this non-reciprocity nature? So of course, the first term, which is inversion symmetry breaking. You all know about it. And then mirror symmetry. And the most important is time reversal symmetry breaking with magnetic field. So these three non-reciprocal magnetotransport requires a chiral lattice and a time reversal breaking symmetry probe, which is magnetic field. Yeah. So let me now sort all current contributions which can affect the voltage usually we measure. And as you can see here, this is very common for us, Ohm's law, and then Hall effect, then this B square term as a function of field, and then the term which I was talking about is this chiral term. So each term has a unique parity signature under I2 minus I and B2 minus B. So as you can see here in this table, I made, so this is the Ohm's law. So parity in I is odd, parity in B is even, and you can sort of see from these, this and this terms how they hold parity. So as you can see here in chirality, this B dot I square term, its parity I is even and parity B is odd. So that is why it requires broken symmetry, which is P, and it shows magnetochiral anisotropy effect. And that is why 2 omega measurement is very important. Now, as I was saying, that this gamma term, which is sort of signature of chirality, it also shows something like, I mean, let's see how it is distinguished from other magnetoresistive ghosts, something like MR, right? You usually measure magnetoresistance as a function of field. So ordinary magnetoresistance, so order in I is 1 and order in B is 2. P is broken? No. So 1 omega, usually we measure 1 omega, which is ordinary magnetoresistance. Of course, Hall, all is 1 and 1 omega transverse. I can guess there are plenty of talks on planar Hall effects. So as you can see, it depends on sin theta cos theta. So the transverse voltage. And now comes our magnetochiral anisotropy, which is order of I is square and order of B is 1 and it's chiral. Having said about this chirality, what type of systems which we are going to probe? It's more of a one-dimensional wear. So these are like nano wears, or you can say ribbons, not like hollow carbon nanotube. So, of course, carbon nanotube is something which is like the most celebrated one in nanowares. But people have worked on quasi 1D materials recently. I also guess that there could be 1 or 2 talks looking at the speakers that on quasi 1D systems. So there are predictions of quasi 1D systems, and as you can understand, if I have a quasi 1D conductor, you apply current, and you can apply different directions field and measure magnetoresistance. If this conductor has some sort of a chiral nature, helicity, then you can measure chiral conductance. Yes, so as I was saying carbon nanotube shows very interesting quantum dot properties, also silicon nanowires, indium arsenide in superconductivity, and graphene nanoribbons. Having said that, the recent ones, the quasi 1D systems, they have also showed very interesting properties like photo-induced charge transfer, quantization of conductance, even Coulomb blockade, and voltage tunable circular photogalvanic effects. All these are already shown in quasi 1D systems. Now our system is tellurium, which is very interestingly can have nanoparticle, 2D and 1D. And people have studied that in different architectures. FET, like field effect transistors, they have made ferroelectric devices, piezoelectric or resistive switching devices, gate tunable systems with tellurium nanowires, and then a lot of papers on paper depositions, how to grow tellurium. Tellurium is group 6 p-type semiconductor with 0.34 optical band gap, and as you can see, there is the trigonal lattice, and then there could be helicity, two helicity, left-handed and right-handed, which is the source of the chirality. And as you can see, these are the nanowire directions. This is the nanowire directions towards the screen, and it shows wild semi-metal characteristics, as you can see here. And along a specific directions, it shows linear dispersion. I guess HL directions in this high symmetry points. So tellurium is still a rich transport platform to understand 1D sort of quantum transport properties. We will try to see weak localization effect in our system, and if we can find negative longitudinal magnetoresistance, which sort of gives some sort of an idea whether it is chiral or achiral, and we will try to probe this with magnetic field and try to see if we can control with proximity. So a local ordering can tune this chiral effect or not. As I was saying, that this tellurium is very interesting when it comes to growth. People who are interested in growth can say this, because substrate temperature you change, the morphology changes, and it depends on the temperature of the substrate you keep. And as you can see here, wares can be formed or large flakes can be made. In our lab, we can grow this tellurium as we wish. So in one go, as you can see here, with chemical vapor deposition, physical vapor deposition, in one slide, we can grow particles, 2D flakes, and wares. So this is just one go. We can create these morphologies. Sorry. So, as I was saying, it can create sheets of tellurine, and also, depending on the temperature, it can create wares. So individual helical chains packed together via weak van der Waals force in this direction in the perpendicular to A and B axis. So whenever we talk about quantum transport, we discuss quantum interference, enhanced correlation, so connected to the density of states, broken symmetries we discussed, and the topological handle if we have. So tellurine has already reported in the literature, while-like nodes, and as you can see here, it has the chiral nature also, and broken symmetries. So our system, coming to the experiment, shows quite prominent feature of one-dimensionality in our nanowires, and it's quite high quality single crystals. Of course, there are native tellurium defects in the system. Now, in terms of magnetoresistance, before starting the measurement, you must have the idea of different things like hole mobility, hole density, effective mass, which is anisotropic, spin orbit coupling of the order of 0.13 electron volt, and the order of onset of linear magnetoresistance. So usually it's narrow band gap, as you can see, radial spin texture, and helical chain geometry. The device is very simple. It is 4-terminal device, and on top of silicon oxide, very conventional, and it shows considerable mobility, and usually our devices are like 20 to 50 to 100 nanometer diameter. The results which we show, it's almost 10 devices which we have measured and got the statistics. So this is quite consistent. As you know, it's p-type also. Tellurine is p-type. So this is the structure. I mean, the representative image of the tellurine device. These are the electrodes, as you can see, and on top, beneath, there is a wire. You might not see it properly, but there is a wire here. So it shows p-type nature. P-type nature, as you can see here, for students, current at the negative gate voltage, it is high, and then there is offstate, and then there is good ohmic contact from linear transport, and then there are a lot of devices with statistics so that we know what type of transport properties we are looking at. It shows p-type because tellurium vacancies are very natural to this tellurium nanowires, and while growing this, we have seen that it's quite unavoidable to get rid of these tellurium vacancies in the system. Usual R versus T as a function of temperature, resistance, and it shows metallic behavior, not a very good metal, as you can see. And then around 40 Kelvin, there is an upturn in the resistance. We are interested in that because we will keep ourselves around that temperature only. So we apply field. Sorry. So when we apply field up perpendicular to the plane of the tube, we see weak localization effect. As you can see, 1.6 Kelvin, weak localization effect with some oscillations around 5 to 10 Tesla. We can fit it to find the phase coherence length, very routine work of this device transport. So magnetic field suppression, so suppressing constructive interference and producing cusp-like positive magnetoconductance, and increasing temperature may reduce L phi, which we should see in our result, as we have seen, as you can see here. So the phase coherence length decreases as a function of temperature. So quantum interference increase. As you go down with temperature, your phase coherence length increases. Coherent time reversed whole trajectory is enhanced, backscattering. So you have more conductance, and phase coherence follows the 1 by root T behavior, which is more of a characteristic of quasi 1D dephasing. Sorry, very sorry. It's very sensitive. Yeah, so this is transverse magnetoresistance. This is longitudinal magnetoresistance. As you can see here, these oscillations only appears when we apply magnetic field out of plane. So in plane, along the axis, let's say, if we apply magnetic field, we don't see any oscillations, and we explain these oscillations in the light of universal conductance fluctuation. So universal conductance fluctuation as a function of angle of the magnetic field is studied, and as you can see, with angle it almost disappears, and we find the autocorrelation of the conductance, which is of the order of E square over h, 0.6 is E square over h. So how does it apply to the basic physics? So every conduction channel give a phase factor, right? So this phase factor gives transmission as a function of t, some mod t square, which is transmission mode, into E square over h. So that is why you see some sort of a scaling with 0.6 E square over h, and correlation field of the order of 1 to 2 Tesla. What will happen if we apply out of plane magnetic field to in plane? So, and the field is 50 Tesla. Now you can see the appearance of oscillations. Of course, after analysis, you would understand that these oscillations are not periodic. So the common guess is not working. Shubnikov-Dihas is not working. There is something aperiodicity in the system. So you can very accurately try to see with the angle what are the oscillations and see if it is consistent. So after 5 runs of magnetic field, we could see the same oscillations for the particular device, and we could confirm that these are real aperiodic oscillations which are coming. So in literature, it has been predicted that quasi-bound states of tellurium, which is coming from the Weil properties of tellurium, which can give you some sort of a aperiodic oscillation as a function of field. Now, with simple language, if we want to understand why these aperiodicity is coming after universal conductance fluctuation. So, if I have a wire and if the charge carriers are moving, while charge carriers are moving, and if it starts to interact with your defects or let's say ions in the system, positive charge carriers, then it would create a bound state, right? So this bound state as a function of field would create a magnetic correlation length, which is very standard 1 by root b. And this length will determine the Coulomb energy, which is E square by 4 pi epsilon LB, which is magnetic length. And if this Coulomb energy is greater than the disorder broadening, which is gamma, which was sort of determining the UCF, the universal conductance fluctuation, then you start to see oscillations. Whenever you start to see oscillations, you should have some sort of this C, which is binding energy, on top of your Landau levels. So it starts to be aperiodic. So whatever Landau levels you have in the system, of course, it will not disappear. You have an extra term which is of the order of C, which is a function of magnetic length, which is a function of B. Now, of course, we have to find the numbers to convince ourselves that there could be some crossover from UCF to this aperiodicity, this magnetic field dependence, quasi-bound states properties. So what we have done, we have found the UCF energy scales, and then we have found the the Coulomb energy, which is quite high, higher than the UCF energy. So around 10 Tesla, we could see that this crossover can happen. So this is the main plot, which is the chiral nature of tellurium. So now we are applying magnetic field along the direction. Now, if we apply the magnetic field, as you can see, as we apply magnetic field, the difference between plus I and minus I increases, and after some field, it goes to it changes sign. So it might happen that after this field, 2028 Tesla, there is this again the dominance of this Weil nature, Weil carrier, and the defect interaction comes into play. We have done all the calculations for finding this parameter of chirality, and it almost matches the theoretical predictions. Now, to conclude, so the idea is in our lab, we could create in situ heterostructures. That was the primary target, to make tellurium heterostructures with the system. Our recent paper shows that we can create very efficient tellurium MOS2. This is just to prove that in the CVD furnace, we can create, without stamping things, we can create heterostructures. And to do so, our most favorite material in the lab is this antiferromagnet. So what we have done, this antiferromagnet and tellurium heterostructure. Why we want to do that? Because for the moment, we are equipped with FePS3's magnon-phonon coupling, which we have understood roughly. And then recently we have tried to understand electron-magnon coupling in FePS3 in graphene. So this sort of data, if we have understood, then why not going a step forward to understand whether spin wave in an van der Waal antiferromagnet can tune the oscillations what we have observed in our tellurine, and if we have observed some aperiodic nature in tellurine's transport, can we tune that to periodic? So this is one of the motivation to start this experiment. We have created our heterostructure and got the first result where we have observed quite a periodic oscillations. So we are, as you can see here, this is the heterostructure and the FePS3 sits here. So the FePS3, the magnet, the antiferromagnet, is in between the voltage probes. So now we can measure the voltage probes in the proximity of antiferromagnet, and we are guessing that this periodicity is coming from the change of the Fermi surface area, cross-sectional Fermi surface area, which is affecting the phase, the frequency of oscillations, and previously what we have observed, the aperiodicity which is coming as a function of field can be tuned if the Fermi surface area has some sort of filtering which would show a single frequency oscillations. So it's an ongoing work, but at least this is quite a reproducible data. At least for 5 devices, we have observed that in the proximity of an antiferromagnet, of course FePS3, because we understand that the aperiodicity is gone. So the take-home message is the phase coherent whole backscattering and the weak localization we have observed in our tellurine nanowire. We have observed the universal conductance fluctuation signature in our field-dependent transport studies, and we have also detected intrinsic electrical magnetochiral anisotropy in our 1D nanowire system. The emergence of high field periodic oscillations in proximity-induced nanowire systems, magnet proximity-induced systems has been observed. Thank you very much.
Thank you, Professor Subhadip. Talk is open for the questions and comments. Thank you, sir, for the wonderful talk. Just a few questions, particularly the experimental side. So, while measuring the second harmonic signal, like what precautions do you take? Because there are some parasitic nurse effects or some Seebeck effects which might hamper your experiment.
Okay, so these are not second harmonic transport, first of all.
Okay.
Of course, second harmonic transport can be measured. People have measured for tellurine platelet like 2D flex systems.
Okay.
2 omega measurement is not simple measurement. Right. So you need to see the V2 omega always. I mean, it's not of the very big voltages you are measuring, right? Yeah. So usually we use in our lab lock-in technique to understand V2 omega.
Okay.
Of course, for tellurine nanowire, I have not seen. Usually, I prefer to measure 2 omega when a phase transition occurs.
Okay.
Around the phase transition, where you can see the change in the voltages.
Okay.
Of course, you have to have your cryostat noise free to understand that, because there could be the very small voltages which you have to measure. You can see our recent paper on tantalum disulfide, where we have explained the process, how to measure V2 omega.
Okay.
In one of the inset of the figure, but you can see the experimental section. Okay?
Yeah, thank you, sir. Any other question or query?
Can I ask one?
Yeah.
Yeah, maybe I here. Let me check, like, if I get it correctly. So you few slides ago you showed a plot like where you said the chirality changes at the high magnetic fields, and that's from the defect effects. You mentioned some
No,
comment.
no, no.
Uh,
A defect will give you defect state will give you the charge. I mean the nature of the charge carrier. So defect comes from p-type defects. So p-type defects will give you the whole nature of the transport. This is first point. Now, why the defects are important in the, let's say, 2 Tesla to 10 Tesla transport regime? Because it might happen that when the wild charge carriers are moving, it usually, I mean, if there is no such defect in the system, disorder in the system, then you would observe usual Shubnikov dehash, right? But you are not observing that. So there could be that there are defects, which is a standard theory in the literature, and those defects in the system is making a bound state. Why? Because there are sluggish electrons which due to this background of defects. Now, if you apply magnetic field, there is a magnetic confinement which is of the order which you can express in terms of a length. So as you can understand, if there is a length, then that binding energy what we are discussing, that E square by 4 pi epsilon 0 whatever, that energy can be reduced. And if that energy is introduced in the with the Landau levels as a function of field, then your whole periodicity is lost. You would see something like cyclotron behavior, h cut omega c n plus half minus some binding energy. And that is why we observe aperiodicity in the system. Yes, sir.
So, technical question for the growth. Do you pre-react and then use CVD, or you put element and then along with the transport agent?
Oh, okay. Yes, I understand your question. I told Bipul to attend this conference. He didn't. He attended graphene. Okay. So, as you can see, so this is the tellurine powder. So this is the tellurine powder, and we put a large silicon wafer, and we know exactly, even if my furnace is a single zone furnace, students have calibrated very well. Yes, they have calibrated really well. So we know roughly of the order of millimeter what is going on. If we know, so now we can map the temperature and then play with this thing. And then, as you know, we have argon flow. Of course, this is very important. Argon flow, controlling the argon flow is very important if I understand well. And then along the length, at least we have understood along the length there is a change. I mean the morphological change. Now, if you ask me question, what happens along the sides? No, I cannot. I know theoretically that these are the parameters which people, diffusion coefficient, supersaturation, vapor pressure, all these are there, but I don't know how to control it.
One more question.
Yes.
That's more general. So, like the weak anti-localization. People feed data and use the 2D model basically. And there is some parameter called alpha.
Yes.
It is supposed to be
Weak anti-localization, yes.
And because we or people use thicker crystals, so they get many papers are there, and the values are instead of 0.5, sometimes it is 100, 1,000, and people
Sure.
say because it is not exactly 2D. So my question is there a 3D model
For the 3D systems?
for the which is applicable for 3D system, because most people use this 2D and then they say, I'm not getting that 0.5 or 1 because my system is not 2D. So my question is there a 3D model? If not, I think our theories, it's a very good problem to put out a theory for some non-2D variant.
Okay, so this is
Not
strictly
exactly question for you, but
so this is strictly 2D phenomena. What you are referring to, I mean the phase thing, right? But to answer your question, the 2D thing gives you 1 by root t, this minus 0.5. Now, do you really care whether people are giving 1,000 and then this?
my question is that
Exactly.
people should not use this model.
Until and unless we have a robust theory for 3D, which is very difficult in my opinion, because because the phase is in a stacked 3D layer. I don't know how can it be, but it can. But the point is, usually it comes from the thin film community. This phase thing. But I won't support a 1,000 or whatever you are telling, that sort of fitting as a standpoint, a standard thing. Yeah.
One last question. Yeah.
Yes.
So one question, like what is the signature of 1D you are getting in the experiment? Like
Okay. So longitudinal magnetic resistance, that is the 1D nature of the system.
So did you measure the system like in plane field under 50 Tesla?
Yes.
And
We have aligned the offset angle, right? It's not easy, but we have tried to make it less than 10 degree, the field, and see the negative LMR, which is sort of a hallmark of that we are measuring something 1D. Negative magnetic resistance, because you are not seeing some oscillations, and with a reasonable field, 50 Tesla is quite a high field, and then if you have negative MR in the chain direction.
I got it.
Yeah.
Just one quick thing, like your critical length, phase coherence length, it's of the order of 60 to 70 nanometer. What you got? It's pretty small, right?
Yes. So yes, a very good question. So to counter that, what we are trying to do is 200 to 400 nanometer lithography to understand that whether we can find some sort of a ballistic transport or not.
Okay.
That is the. Yeah.
Thank you, Professor Dutta, once again.